Okay, guys. Um, Welcome to the fourth edition of Optimal Control and Reinforcement Learning, affectionately known as OCRL. Um, I'm Zach, and super psyched to be here. Thanks everybody for showing up. Let's see. Here are the your course team for the semester. Kevin Tracy, who is with us in spirit and on Zoom, uh, is the lead TA, who's now on his like third round of TAing this class, and probably knows most of the stuff better than me at this point. So he's excellent. And Kevin's also going to run recitations for us on Fridays. So you should check those out if you need a little extra. I mean, it's Kevin's super sharp and an awesome dude. So you should check out the recitations, you know, probably anyway, if because he'll have like a slightly different take than me about some things and kind of go a little deeper into some things than I will in class too. So, you know, recommend checking out the recitations. They're going to be Friday 11 on Zoom. And then everybody else here is local and in the room. You can say hi. So JJ's also on his second round, TAing the course, and solid guy. That's JJ back there. Fausto's back there too. Fausto's first time TAing the course, but took it and also knows what he's doing. Arun, same story. And Sam, everybody's here. So those are your TAs. That's the TA section right there at the back. So hopefully you'll get to know these guys in office hours and stuff. And they're all in my lab and do this stuff, for fun and all that. And it should be, able to help you out. So that's us. And I guess I wanted to first kick off with like just a kind of a discussion about, why. So I think this stuff is like the coolest stuff ever, which is why I do it. Uh, you know, I've basically devoted to my life to this topic, but I wanted to like kind of first just tease a little bit of kind of what this stuff is for and what we do with optimal control in practice and some of the cool things. So the first one, which is like where my first love and like how I got into this stuff is space stuff. So this is actually kind of the birthplace of a lot of this subject. It came out of the aerospace world in like the 50s and 60s, namely in like getting to the moon. And so, more recent times, like the tools we're going to talk about are what's used by JPL and folks like that to design and then fly trajectories to Mars, for instance, like you see there as the Mars 2020 trajectory to get to the moon. And the tools that are typically used for this kind of stuff are direct collocation, which we're going to do in class. And we've had a couple groups in the past couple of years do their course projects on stuff like this, like designing interplanetary trajectories for like a Mars mission or whatever. So this is stuff like, again, yeah, like you can do this by the end of the class. It's like one of the kind of areas the stuff gets used a lot. And again, one of the like original motivators for this whole topic, which is super cool. Other recent awesomeness in the sort of space realm, which I'm sure everyone has seen. This is, SpaceX landing one of its booster stages, first stage of the Falcon 9 on a barge. It's insane to watch this just because of how fast it happens. Like it's surprisingly quick. So anyone know how they do this? Like what the kind of high level like controls stuff in there is? So there's a lot going on there, but the top level of the control stack is convex model predictive control is kind of which we're going to do in the class also. And some of the really seminal results in our field in the last like decade were kind of behind this. There's a really, really awesome paper first came out around 2013. There were some follow-ups by two guys, Bechet Chickmashay, who's a professor at University of Washington, and Lars Blackmore, who at the time was at JPL, but he's now the guidance, navigation, and control like lead at SpaceX. And they came up with this paper deriving a convex formulation of the rocket soft landing problem, which is a very obviously like nonlinear, non-convex thing. They come up with this what they call lossless convexification of this problem. It lets you do this by solving convex optimization problems, which you can like solve with guarantees online really fast and all that good stuff. And that's kind of what's enabled this and also the Mars landing stuff. Again, that's like 10-year-old results. That was a theory paper from 10 years ago that now is, out there in the wild, like doing this stuff, landing on Mars and all kinds of awesomeness. So super cool stuff, landing rockets. We're actually going to do this in class too as a case study towards the end of the semester and give you a little taste for how that like convexification trick works. What else? Autonomous driving. This stuff, has obviously been super hot in recent years. Arguably, like the hard part of all this driving stuff is perception and trying to figure out what the hell other humans are doing when they do stupid things on the road. But the controls part of this is all, for the most part, nonlinear MPC. So typically for stuff like this, where it's relatively benign driving on the road, it's pretty standard to use like a bicycle model for the car and just do nonlinear MPC. A lot of like iterative LQR kind of ideas and stuff like this is getting used in industry for this stuff. There's a lot on top of that, right, to reason about obstacle avoidance and path planning and all this other stuff. But once you go a little bit down farther in the stack and you get to the actual controls side of it, there's a lot of, again, nonlinear MPC with bicycle models and tricks for collision avoidance kind of stuff that's behind all this stuff. And we're also going to talk a little bit about that in class later. So yeah, autonomous driving, and then all kinds of awesome stuff in the last like decade or so on quadrupeds. And this stuff is, I don't know how this stuff works. Check out the quadruped stuff. This is weirdly enough, again, mostly convex MPC. And you look at this thing and you're like, this is super gross and nonlinear and high dimensional. Like, how do you end up using like solving essentially quadratic programs to do this stuff? There's lots of tricks and model simplifications that go into this, but essentially most of these robots, they use what's sometimes called a potato model, where they sort of like assume that it's a single rigid body and ignore the mass of the legs and like do all these kind of simplifications to get you down to something that's like a single rigid body and linearized, where you can do convex MPC. But yeah, most of this stuff is convex MPC also, which we're going to do in class. And we'll do like some case study stuff for like robots and kind of show you how that stuff works a little bit. And then, yeah, got to kick the robot. That's obligatory, right? And then, yeah, I'm sure you guys have all, in the last several years, watched the Boston Dynamics stuff, which is amazing. This is their most recent, well, I guess they had a holiday video that came out. This is like kind of the most recent stuff where they're having Atlas like pick up tool bags and throw things, and we'll just watch it because it's awesome. Anyway, so has anyone checked out the like recent-ish talks from these guys about how they've actually started to like give decent amount of public talks where they talk about how they're actually doing this stuff, and like they have some blog posts online that are pretty good, and there's a handful of talks from the last year or two from like Cora last couple of years where Scott Kindersma, who leads a lot of this stuff, talks in a decent amount of detail about how they're doing it. Has anyone checked out any of that stuff? You should, because it's awesome. So this is nonlinear MPC. This is what these guys are doing. So they're basically using the real innovations here on the control side, and like why this stuff is incredible and like these guys are better than everyone else essentially, is they're using whole body dynamics models. So they have we mentioned like Cheetah, they're doing these simplified potato models where they ignore the leg mass and it's just a single rigid body and they do all this linearizing. In here, they have a full model of the entire robot, all the links, all the joints, all the inertia for everything, because you have to here because the links are heavy, right? And they're taking that entire thing, which is highly nonlinear, and they're doing MPC at real-time rates for that entire thing, which is insane. Computationally, that's really, really hard to do. And like the implementation to do that is next level. Like it's really, really insane. And basically no one else can do this right now. But like in principle, the ideas are like exactly the stuff we're going to talk about in this class. Like the ideas are, everyone knows the basics, right? It's just like the implementation is crazy good here. Yeah. I mean, there's definitely their hardware is really good, right? But also on the control side, they're also really, really good, like the best, like they're, and it's again, like the ideas are all out there. Like they're not like, I don't think there's any like secret sauce, math, kind of stuff. It's all like stuff that like, we kind of know how to do that, like is more or less the stuff we're going to talk about in here. It's just that it's been, the software engineering, the implementation, like really, really is dialed. So I think it's basically taking a lot of really smart controls engineers and like having them bang on this problem full time for like 5 years, to get to that. So it's incredibly impressive, and like no one else can match this, right? But yeah, I don't think there's any like magic that they are, that they know about. There's no like control theory or math magic there. It's all like kind of the straightforward stuff we know how to do. It's just been implemented and dialed to like the nth degree, right? Anyway, yeah. So this is all awesome. Love watching this stuff. But let's just watch the video. So good. It's so insane. Like it almost doesn't look real. Like, doesn't this look like computer animation? Like it doesn't look real when I watch this. It's so nuts. but I've seen this in real life, so I know it's real. All right, cool. Okay, so yeah, so that's like stuff in the last, say, 10 years or so that's been like kind of, risen the bar, I would say, in our field. And like we're going to talk about all the things I just teased in the class pretty explicitly. We're going to like go through, kind of some of the space stuff, the direct collocation stuff, some driving stuff, a bunch of legged robot stuff, and kind of show you some of the tricks, and like kind of get you pretty close to where at least you can like read the papers and be up to the state of the art, in the literature, and then kind of where, like I guess from my perspective, a little bit where the challenges are, right? Where are we still struggling? Where are the next steps, and where are the hard research problems? One big one in robotics for us is dealing with contact. So like all those legged robot videos we just watched, you're like, slamming into the ground, making and breaking contact, like picking things up. All these kind of things result in discontinuous dynamics where your dynamics are non-smooth, right? Non-differentiable. You have these impacts and stuff. That makes all this stuff really, really hard. It breaks all like kind of your gradient-based optimization tools. It really messes you up, and you kind of can't do a lot of the normal calculus things that we like to do. So that stuff's still really, really hard and kind of a core robotics controls challenge, I would say, at a very deep level. Another one is that, it's reinforcement learning is in the course title. Spoiler, like this is an optimal control class. I would say like at a high level, they're the same thing. This is my take. And I think the stuff I'm going to try to really dive into here is what I think are like the fundamentals. Like the two subjects are, they're trying to address the same set of problems, and the underlying theory is the same. It's basically like the algorithmic tools we use to attack things, right? So in optimal control, I would say at a high level, the difference is in optimal control, we tend to Taylor expand and use polynomials, and in RL, we tend to use neural networks. So it's like pick your favorite function approximator, but like that's like only half. That's kind of true, but like the deep stuff is the same. So we're going to talk about like value functions, dynamic programming, all that kind of stuff. And I think like I'd argue you really should know these like fundamentals to know when to pick one or the other. So I think like hopefully this is going to give you a solid like base level of understanding of the basic concepts, that are applicable to both sort of areas. And we'll talk a little bit about some RL topics, but the primary focus here is on like the really, really basic like optimal control, sort of dynamic program kind of ideas. But yeah, like I think right now there's a huge gap between the communities. There's like a bunch of people who came from like computer science who are doing reinforcement learning now on hardware, on robots, which is awesome. But they come from this lineage from computer science of like, um, I don't know, like mostly things that are done in discrete state and action spaces and like a different set of algorithmic ideas and tools. And then you got the control community that's coming mostly from engineering, from like aerospace and mechanical engineering and whatever, where people are used to like living in continuous time, continuous state and action spaces and thinking about ODEs and stuff like this. And there's a huge mismatch in the language and tools. But I think like increasingly these things are kind of butting up against each other in the real world. And like there's a huge need to like bridge the gaps and sort of figure out where the connections are and stuff. And I think it's a huge opportunity for all of you guys to like, go take this class and then go take Deepak's class, for instance, and like be the ones to glue these things together and bridge the gaps. So that's a huge thing, where I think it's mostly that we're like talking past each other and don't speak the same language and use different notation and stuff like this. And there's not enough people who know both sides well enough to like bridge. So you guys should do that. Okay, and then another one that I think is again super applicable both sides. Again, like um, right now, a lot of the RL stuff is very black boxy and like assumes very little of the system or the environment and just uses data alone, and that makes it pretty data inefficient. Whereas in a lot of cases, we know quite a bit about the system, about the environment, blah blah blah, and we have strong priors. And I haven't seen enough work, I think, like bridging those gaps. Right, we want to like, from my perspective as an engineer, you should want to like, you know, use the models where they're good and then use the data where the models are bad and sort of to be more efficient with the amount of data you need and all kind of stuff. And I think bridging that gap and like kind of thinking about these things, that's where I think, model-based optimal control, which what we're going to do, like is extremely efficient, right? Whereas, and that's kind of what it brings. And also has like nice, strong theoretical guarantees in a lot of cases that we don't yet know how to get with the RL tools. So I think there's like good stuff on both sides. Then another one, in aerospace, where I come from originally, like safety guarantees are a huge deal. And so for like nonlinear systems with uncertainties, this is really hard. And this is kind of one of the areas right now where, RL is currently lacking in a lot of these kind of things. So figuring out how to get those kind of like safety guarantees, like if you're flying an airplane or trying to land a rocket, like these are important things, and things get expensive and human lives are on the line. And I think this is one of the things that's going to hold up a lot of the RL stuff from getting fielded in safety critical applications, right? And then yeah, like the last one here, kind of poking at like some of these driving scenarios. I think this stuff's really cool. We've done a little work on this in the lab too. But dealing with like other agents that are not necessarily cooperative. So the big one where this shows up and why this has become a thing recently is in driving, right? Where you've got to reason about what other human drivers might be doing, their intent, their behavior. This goes under sometimes the name inverse optimal control, inverse RL. It's also like related to game theory, and we'll talk a little bit about this kind of stuff. But I think there's really cool stuff in there, and this gets into HRI and all kinds of other areas. But it's a very rich area. And these are just some like things to throw out there that you guys might think about for like your own research. Class projects, stuff to check out where there's like gaping holes that, stuff we really don't know how to do yet. Okay, so that's some survey of topics and random thoughts about the field, and then a little bit more bringing home to like what we're doing in the class. So there's a class about optimization based control techniques. So we're going to talk a lot about dynamics, a lot about numerical optimization, and then sort of how you use those things to control robots and they can do stuff that you want, right? We're going to focus really, it's pretty application heavy. Like we're going to do lots of math and whatever, but it's not a theorem proof lemma type class. This is a code it up, make it work kind of class. So we're really going to focus on like the applications and the robotics side of it rather than theory stuff. And the homeworks are going to be focused on implementing the algorithm. So the homeworks are all going to be like Jupyter, coded up kind of things. Run the algorithms in sim, watch the robot do cool stuff in a visualizer, that kind of stuff. There's going to be, I say approximately there's 4 real homeworks. There's one homework 0 that's going to go out Thursday. That's really like hey, if you don't know this, you should do some like little homework to fill in some gaps, and we'll have some recitations on this stuff. That one's mostly for calibration. It's not really going to count. It's mostly just so if you don't know these things, you should like, here's some resources, show up to office hours, show up to the recitations to fill in some gaps in your background, right? So that's homework stuff. And then this project doesn't have any exams. It has the 4 homeworks and has a final project. The final project is, basically do something cool. Hopefully, so you guys are grad students and working on either master's projects or PhD research where there's a reason you're here and you like are into this for researchy reasons for your own stuff. And so, do something that's relevant to you. Don't do busy work nonsense. And I'd say like I think we've generally wanted to keep do this in groups, right? Do it with your friends, do it with people who like. You can do it by yourself if you really want to, but I'd suggest working with friends better. And I think we want to keep the groups to like 3 to 5. I'd say is a good size group. I think 2 people's fine. 5's getting a little big, but that's what we're looking for. And in a couple of weeks, like I think part of the first homework, we're going to ask you guys to like propose your group, like basically figure out your groups and propose project ideas. We'll give you some ideas for this stuff, like maybe a list of like idea top. But the idea is like really you should do something you're into, and it's super wide open. It can be anything, just that like uses ideas from the class, right? That's got some component of like reinforcement learning, control, MPC, anything optimization-y, right? It's just stuff that's you're into, that's your own thing. The idea is hopefully this can like lead to a conference paper, right? For those of you who are master's and PhD students. Cool. And then kind of logisticsy stuff. You found this room. It was hard, but this is where we're at, 5:00 on Tuesdays and Thursdays. I also will like stream the stuff on Zoom. I'm also recording everything, like the notes and the videos and everything will get recorded and posted online. Recitations will be on Zoom Fridays at 11. You should check those out. They're not required, but recommended to check them out. We've got a Piazza that we're gonna use for all the communication stuff. So if you need to like message anybody, any of the TAs, me, whatever, Piazza, yeah. Yeah, they'll also be recorded. Yeah, we're gonna like try to make this as easy. I have no interest in like forcing anyone to like listen to me talk if you don't want to. I don't care. So like everything's gonna get recorded, everything we posted. I like you guys. You should come hang out. But like if you've got like if you're sick, if you've got other things going on, whatever, I don't care. Like we're all like pretending to be adults here, like it's all good. Like it'll be on YouTube. You can stream it on Zoom if you want to. I don't need you to be like, I'm okay with you like not staring at me for an hour and a half or whatever. So yeah, we'll post everything. Piazza, check that out. And then what else? We're going to use GitHub and Gradescope so they're going to be coding assignments. Um, you should, yeah, you definitely need a GitHub account to like get the assignments, and then you'll like upload them. So blah blah blah. So you should have a GitHub account. If you don't, go get one. And then office hours, we're going to send out some polls, try to figure out what good times are for people for office hours and whatever, set a bunch of those up. We should be able to give like pretty good coverage because we've got 5 TAs plus me. So should be pretty good on that front. Any questions about anything? Yeah, that is coming. Okay, so let's get into that. So first off, I'll like do this in a sec, but there's a course survey, which is like a little Google form thing that I'm just like asking you random questions about like stuff you've done before and just trying to poll to like calibrate a little bit. And then this is the Piazza that you should sign up for. Um, the easier thing to remember rather than typing those in is the course website, which it took me about like 4 or 5 months to get this to happen, but I got them to give me this URL, which is nice and easy to remember, which is optimalcontrol.ri.cmu.edu. And thanks to Kevin, we have this nice website now. So this has everything. So like just go to this website. All the links are here. Everything should be here. So you got the Piazza, Canvas, which I don't think we're ever going to use, really. Gradescope, GitHub, YouTube. So all of it's here. The syllabus is here, right here. Everything's, there. I mean, everything you need should be here. Um, yeah. So go to that website. Everything else should kind of follow from there. You should be able to find it, here. A couple quick things. So this is the GitHub org. You guys are all going to end up getting your homework and stuff on here, but I'll show you a few things. Um, the lecture notebooks are going to get posted here. There's a repo called Lecture Notebooks. That's where the notes are going to be, and I'll do like a bunch of live code stuff in Jupyter Notebooks. Those get posted here. You can see last year's and the year before on here if you're curious and want to kind of like poke around a little bit. So if you go in here, like this is it. You've got all the content. So if you want to go like, get a sneak peek and or whatever, look ahead for like projecty stuff or anything, feel free. It's all there. So you can like, for example, I don't know, go in here. There'll be like the PDF of the notes and then the Jupyter notebook. So you can like run the code from class, kind of stuff. So that's all there. I'm going to do the same thing this year. So like there'll be this year's lecture notebooks and like lecture one will be up tonight. What else? The syllabus is in here. Maybe take a quick look at that. I think I already have that open. So here you go. I don't think there should be anything surprising in here. I think I said all this stuff already. But yeah, just go to the website. It's on the website. Project stuff, schedule. This should be fairly accurate. There's going to be probably some moving around of some stuff based on like how things go, but that's kind of the scheduled topics. So we're going to do a bunch of like background stuff on dynamics. So this is in the Google form, so I don't have to ask you right now, but like how many of you guys are like CSRI type people? Like, and then mechies. Actually, yeah, good number of mechies. Okay, so some people here know how to do dynamics. That's helpful. Like the problem here is we got to do dynamics like crash course for all the CS people. We got to do like programming crash course for all the mechie people. Like there's a little of that going on. Cool. And then the ECEs. Anybody else that doesn't fit into one of those buckets? Yeah. Oh, you're EC. Anybody who's not any of the things that I said? Okay, so everybody's like RI, CS, Mechie or EC. Cool. Last year we had some chemies, which is also cool. Okay, cool. yeah, so that's kind of it. Let's see, anything else here? So that's this stuff. Okay, so yeah, this is a course survey. It's like asking you a few basic questions about like your background and stuff. I will say right out the gate, um, everything in the class can be in Julia, which is the most polarizing thing about the class, maybe. It's really like uh, yeah, I find it so I hate Pythons. I hate NumPy. Like I hate doing matrix math in Python. Who decided to make an at symbol mean multiplication? Doesn't make any sense. So Julia is sort of like kind of MATLAB Python. It's a high level language, very easy to use. Like it's really nice to write matrix math in it. It's a little bit more MATLAB in terms of how it looks. You can almost copy paste MATLAB code into it. So if you're familiar with MATLAB, should be right at home. It's also like very close to Python. We're going to use Jupyter. You can run Julia code in Jupyter notebooks. So if you've like played with either Python or MATLAB and you haven't seen Julia before, it should be a very easy adjustment. It's not a big deal. And again, like the stuff we're going to do in class is not using like fancy language features. It's like basically doing linear algebra. So I find Julia to be the best language for doing linear algebra. And that's kind of why we're using it. Um, yeah, so that's kind of that. What else? A couple other things. Oh yeah, so I have this like anonymous feedback form also that like, all this stuff's in the course website, blah, blah, blah. So the reason for this is that I found like some people, so first of all, you should feel free to like yell at me and tell me I'm doing things badly and stuff and like generally give me feedback. I think all reasonable here. If there's something that that's bothering you, that for whatever reason you feel uncomfortable, telling me to my face, I'm fine with that. I'll put it here, totally anonymous. I won't know who it's from. So if you want to tell me, that I'm ugly or whatever, this is fine. I don't mind. Seriously though, yeah. So that's all there. So you can like, if there's anything, that like is sensitive or whatever, you can tell me there. And then Piazza's up here. Again, the links are there. Sign up, whatever. This is where we're going to put announcements. And like, if you need to bug anyone, I used to use Slack, which I liked, but the class got too big for that. So now we're doing this. Cool. I think that's it for logistics stuff. Um, I think aspirationally, we're going to put links to all the lecture content in here, like in the syllabus. So you should be able to get it all here. But if not, there's a YouTube channel, which I'll show you what it looked like last year. This is the lab YouTube channel. And then here's last year's playlist. So just all the lecture videos and all the recitation videos are in here, like chronologically. So you can also look at last year's stuff if you want. Generally, I'll post the stuff in there within like 2 days. It sometimes takes a little time to like edit some stuff. Okay, cool.
Zach, if you want to go to the lectures from last year, the lectures tab in the website has everything organized.
Neat. Yeah. I knew that was there. But yeah, so we're going to do that again this year. Lectures. Where's lectures? Ah, there we go.
On the top, yeah.
Oh, yeah, so this is like last year's content. So we'll do the same thing this year. So it's all nicely organized. So you got your YouTube link, the like slides and code, the GitHub, all that good stuff. All right, cool. Anything, questions, comments, thoughts? Feeling good about this stuff? All right, excellent. Now we can do stuff. I will. Oh, this is annoying. Like chops off the. Okay, so we think we're good on this stuff. Excellent. All right, so let's get into it then. So, as a sort of to ease ourselves into all this craziness, is this working? Yeah. Also, yeah, like if you can't hear me, if there's weird issues with this thing, this room is much better and it seems to have good Wi-Fi. The common problem last year was that like the whole Zoom tablet stuff would freeze and crash semi-often. So if this happens, yell at me. Hopefully we're okay. All right, so first order of business and like kind of where we're going to start things off, just as like a little background review kind of thing, is to talk a little bit about dynamics. And if you've never taken dynamics before, if you're a CS type of person who's never seen a differential equation in your life, don't worry. One of the big things in here is that we're going to do pretty much everything in discrete time. So you really don't need to know anything about like F equals ma, Lagrange's equations, ODE stuff. What I'm going to do for the first couple of days here, we're going to give you like a little crash course, just get you enough so you can like make it through the class with what we're going to need. Just a little background stuff, all right? Again, speak up, just yell if you have questions. Like I will, if it becomes a problem, we'll fix it, but I think we're fine. So yeah, so we're going to talk a little bit about continuous time dynamics today. and very high level. And then next time we're going to basically talk about how you discretize these things to get like discrete time dynamics. And when I say discretize, I mean like ODE solver integrator stuff like Runge-Kutta methods, that kind of thing. So we'll talk a little bit about that next time. Basically, just enough so you know that like, okay, there's differential equations for these things, and then we turn them into discrete time, maps that we use for numerical stuff on the computer. Okay, so we'll start off with like the most kind of general slash generic um, uh, setup for a smooth dynamical system. And this we'll clarify what I mean by, so when I say smooth there, I mean that it doesn't involve, from a robotics perspective, what that really means is it doesn't involve contact. As soon as I do like that, that's non-smooth. And I slam into the ground, and I can't really do this anymore. But so for things like, I don't know, drones, anything that's like not slamming into stuff and doing contact switching, you can kind of do this. So here's kind of the generic setup. X dot equals f of x comma u. So we refer to colors here. So this is called, F here is called the dynamics. X is called the state vector, or we'll just call state. And usually we assume that this is a vector in like Rn. It isn't always, and we'll talk about this in a sec. And then U is our input or our control. And usually we consider this a vector in Rm. And then this x dot is the time derivative of the state, right? So the dynamics function is the thing that takes your current state and your controls and tells you like which way the system's going to move, right? That's cool. And so for a mechanical system, which are most of the things we're going to talk about in robotics, though, there's plenty of things where it's not a mechanical system, like electrical power grids or whatever. There's all kinds of other non-mechanical systems. But for us, in the robotics context, mostly we're talking about robots that are mechanical systems. You have the following kind of setup for the state vector. So this state X, again, for like most robots, is going to involve kind of two pieces that we're going to call Q and V, where Q is called the configuration, or sometimes pose. So that's kind of like, think about it as position, right? This thing, importantly, is not always a vector, which I'll explain this in a sec. And then this thing, the V, is, as you might expect, the velocity. That's usually what this looks like for a robot, right? So the Q for like, I don't know, for a legged robot, that would include like the center of mass position, the orientation of the body as a quaternion or rotation matrix or something like this, and then all the joint angles for the limbs. That would be a pretty typical like configuration vector or like a humanoid or something. And then the velocity would include like the linear velocity of the CG, the angular velocity of the trunk, and then the joint angle derivatives, the Q dots, right, for all the joint angles. That'd be a pretty typical sort of state vector for like a big robot, right? Any questions about this so far? Who's done this stuff before? Okay, so like half, decent number who haven't done this stuff before. Okay. All right. So an example, like to put this stuff into like concrete, kind of terms, um, the classic, everyone's favorite nonlinear system, we'll do a pendulum. So draw a bad picture. Um, you got mass, we've got an angle theta, and we've got like length L here. Oops. And, pick your favorite, freshman physics method for this. Like you can use F equals ma, you can use the Euler-Lagrange equations, like whatever. But if you kind of stare at that for a minute, I'm sure everyone's seen a pendulum before in their lives, right? Uh, freshman physics, the equation of motion of this guy, if you do some F equals ma, is the following: ml squared theta double dot plus mgl sine theta equals equals the torque applied at the joint up there. And so for our purposes, so here's like your F equals ma stuff that you can go back to your freshman physics textbook or Wikipedia for this kind of stuff. So we're going to now kind of put this into the x dot equals f of xu form, and just to kind of show you what that looks like. So the state vector x here is going to be the configuration or pose. So for us here, that's just theta. And then the velocity is the theta dot. So that's our state. So here to be, I should say Q equals theta, V equals theta dot, and then our control U is that torque. So we're going to kind of put it into that generic setup. That's our X. And then if I kind of write out all the stuff, we have X dot is going to be theta dot, theta double dot, and then we just kind of massage everything in that equation into this kind of generic form. So theta dot is just theta dot. That's already part of the state vector, so that's kind of trivial. And then the second line of this, I'm just going to take that equation there and like kind of move stuff around and solve it for theta double dot. So that's going to be minus g over L sine theta plus 1 over m squared u. Okay, so this thing here, this is our f of x comma u. Cool. Any questions about that? And the reason this is a thing, first of all, that like generic f of x u thing, that's used in all the control literature. Like that's how we like kind of generically talk about dynamics. The other reason you should know about this and like how to set up this state vector thing and why we stack everything up like this is the standard format when you go on a computer and you try to simulate a system like this. All of the ODE solver toolboxes like, MATLAB and which ODE 45 and MATLAB, if you use that, or differential equations.jl, which is the Julia one we use, they all expect this like x dot equals f of x format. That's what the API is. That's like the standard thing. So you got to do whatever you have to do the physics. And then when you've got your physics, you kind of end up always needing to massage it into this first order vector ODE format where it looks like x dot equals f of x or f of xu like we've got here. Cool. Questions? Okay, so here's a fun brain teaser. So we said, that this configuration or like pose thing Q here, like we often think about it as a vector, but it's not really always a vector. And in fact, we've already got one of those scenarios here. So question, what is the configuration space for a pendulum? Is it really like, so it's a 1D thing, right? It's that theta. Is it really a vector though? Is it really a vector space? Is it really like arc? What is it? The circle. Yeah, you got it. So we're already right out the gate for like one of the most basic things you can, talk about dynamics for. This is already not living in a vector space. So the configuration space here is, for being fancy, you call this S1. That's the circle. So next question is, if that's Q, remember the state space is now like Q and V, right? This 2D thing, theta theta. What's the state space? So that's the configuration space. It's a circle. Does anyone like have any thoughts on what the full state space looks like? Yeah, yeah. So where'd you learn that? Yeah. That's right. That's right. So the configuration of the Q lives on a circle, but the velocities actually can be anything, right? So the theta dot can be whatever. So theta dot is actually in R, right? But the way to think about it is you've got this circle for theta. At any given point on the circle, R can be anything. So you've got a tangent line basically at every point on the circle. So if you're a topologist and you don't care about, whatever, if you're kind of loose about this, you can think about taking those tangent lines and spinning them around like this. So now what you have is a line attached to every point on the circle, which forms a cylinder. So topologically, the state space for this guy is actually a cylinder. The way you write that down in like weird topology kind of land is S1 cross R. That says at every point on the circle for every Q, you've also got an R. That's called the Cartesian product. I don't know. I don't know what it's called. So this is a cylinder. This is just, for fun. You don't have to know this stuff. This is just me being a weirdo and liking differential geometry. You don't have to. Okay, cool. Any questions about this stuff? Okay. So next up, so that's kind of the most generic form for a smooth dynamic system. This is like super, super standard stuff. And this is kind of the format you're going to use in most cases. We're going to assume something that looks like this. But there's a few other, there's some, if you go sort of peel the onion, there's more types of dynamics functions that show up that have more structure. And usually more structure is good from a control perspective. Like you can leverage that structure to make your life easier and be clever. So we're going to peel back the layers a little bit. So a little bit less general, a little bit more specific than the form we just wrote are so-called control affine systems. So what these look like is rather than x dot equals f of x comma u, where everything's nonlinear, these look like x dot equals, we're going to call it f naught of x. So you have a nonlinear term in the state, and then you've got what we're going to call b of x. So that's a matrix, that's a Jacobian matrix, times u. So the idea here is this thing is nonlinear. It's nonlinear in x, right? That f naught could be anything, but it's u shows up linearly, right? Like u shows up multiplied by that b. That b can be any function of x you want. So b can be a nonlinear function of x, but this whole thing is as a function of u, it's linear in u, or it's affine. As a function of just u shows up linearly plus a constant term, as far as u is concerned. That's a term. That makes sense? That's called control affine. It's the affine in u. And then there's names for these guys. So this f naught thing is called the drift term. And then this b of x guy is called your input Jacobian. It turns out that a lot of things actually have this control affine structure. In particular, all mechanical systems are control affine. So in a lot of robotics contexts, you can actually kind of deal with control affine systems. So we'll even say like most systems we care about can be put in this form. There's a trivial way. If you have a generic like f of x comma u, there's a trivial way to turn that into a control affine system, which is kind of dumb. It's to take the u that you had, augment the state vector. So you take your original x, you stack u in there, and then you make a new u that's the old u dot. Basically add an integrator to the dynamic. And now you've got a new thing that's control affine and what would have previously been u dot, which is like kind of a trivial trick, but I don't know. Okay, so we can stick our pendulum in this setup. And in that case, the f of f naught would look like theta dot. So this is all the stuff that doesn't depend on u from up here, right? So I just take this guy and I take out all the stuff that doesn't have a u and put that in f naught. I get theta dot and then minus g over L sine theta. So it's nonlinear in theta. But if I kind of look up here at the u term, just got this constant multiplying it right in front of it. So that's our b. So the b of x in this case is constant, doesn't really depend on x, and it's just u. This top is 0, and then this guy is 1 over m squared. Cool. So control affine shows up a lot actually. Sometimes is useful. Questions about that? Ooh. Okay. The next more specific dynamic setup that you will see that is extremely common in robotics are called manipulator dynamics. And all of you like RI types should have seen this before, and mostly ME types should have probably too. Has anyone not seen the manipulator equation before? Everybody. Oh, not you. Okay. So you're good. We got you. But most people see this. So okay, this looks like the following. I'll write it down, then I'll like label the pieces. Um, okay, so what do we got here? So the M up here is called the mass matrix, or generalized inertia tensor, if you want to be fancy. Um, the C is called sometimes goes by, these things all have multiple names. This is called the dynamics bias sometimes. Um, it's also sometimes called like the Coriolis term, but often like you'll see this written a few different ways. But the C thing is called dynamic bias. It often includes like Coriolis stuff, and or sometimes people separate the Coriolis terms and the gravity terms and whatever. So there's a few ways to write this, but we'll keep it simple and do this way. This typically includes like Coriolis forces and like gravity terms. And then the B again is called the input Jacobian. And is the how you map your controls into the dynamics. And then the F is basically any other forces. So typically that would include like friction, drag, anything dissipative, contact forces, all the other stuff. So we'll just call that like external forces. Okay, so that's the first part. And note that, the thing in here where this is, so I guess two things to say about this. One is this is sort of like a vector generalization of F equals MA, right? It's like a fancier way to write F equals MA. The note that I wrote double dot, and there's a specific reason I did that. It's because we're also going to talk about a second piece of this guy down here where we write Q dot equals G of Q times V. So some people do it this way, some people don't. We're going to do it this way. And this goes back to that whole spiel about the configuration in general is not a vector. Where this specifically shows up for us, and like all robotics people should be on board with me here, is you do anything with 3D rotations, you need it to look like this. The reason is your configuration now has to be something like a quaternion or a rotation matrix, or if you're particularly sadistic, Euler angles. Never use Euler angles. In any of those cases, no matter what you pick for your 3D pose representation, your velocities are never the time derivative of that. Like your velocity is always going to be like omega, right? Like angular velocity. Turns out you can't integrate omega in any straightforward way that's meaningful. You always have some Jacobian thing there that's mapping omega into whatever your Q dot variables are, whether they're Euler angles, quaternion derivative, rotation matrix derivative. So that's kind of why I'm harping on this and making a big deal about it. In general, this is always the case. You always need this second piece here. And we'll just call this, this guy, the velocity kinematics. And this setup's pretty general. So I guess a few things to say about this. First of all the like standard robotics toolboxes will give you this stuff. Like there's all kinds of, toolboxes where you can give it a model of the robot in the form of like a URDF file or something like this, and it'll spit out these terms for you, so that you don't have to handwrite the dynamics and do F equals MA on some heinous, complicated, high-dimensional robot. So you should use those toolboxes. This is what they're going to give you, which is kind of why we're talking about it. So if you have one of those toolboxes and you've got if it's giving you like MCB, blah, 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 and you want to write it as x dot equals f of xu, like we've talked about. Here's how you do that. So we can take this stuff and we can turn it into to this form. So we've got the q dot stuff, just looks like g of q times v, right? That's q dot. And then the v dot stuff, we just take our manipulator equation up there and we solve it for v dot. So that's easy. You just take m inverse times all the other stuff, right? So um, cool. Yeah. Yeah. So this is subtle. This is one of the, again, me harping on the whole like the pose isn't always a vector, blah, blah, blah. If you're not, if you make good choices, M is always invertible. There's situations in which M can be singular. Those situations are situations where you've chosen your coordinates poorly. So if you use minimal coordinates in particular, and there's, so if your number of velocity variables is equal to the number of degrees of freedom of the system, then M will be invertible every time. So M will have the same dimension as your velocities, and M will, as long as you use like minimal set of velocity variables, it's guaranteed to be symmetric positive definite. There's sort of other gotchas in there, some details we can talk about. But yeah, that's kind of the deal. If you make good choices, it's always invertible. Also, you probably shouldn't do this in prep, but like this is fine to do, but there's smarter ways to do it. So in particular, here's why. Do you know like the complexity of this thing, big O? If I asked you like, what's the complexity of those? So you're solving a linear system, like matrix inverse, vector thing. Does anyone know what that costs you in terms of flops or whatever, like big O? It's n cubed. So like if your dimension of your state vector is n, doing this is n cubed. It turns out that, so that's, for a big robot, that's sort of expensive. Um, so like, if you have a 100-dimensional state vector for like Atlas, it's, 100 cubed, not awesome. Turns out for many, many robotic systems, there's smarter, clever ways you can do this that are OS or linear instead of cubic. It is famously called like Featherstone's algorithm, the recursive Newton-Euler algorithm. People have maybe heard of these things. So that's like the better way to do this. And a lot of these toolboxes will do it for you. But if you need to in a bind, you can do this. And as long as the system's not huge and you don't care about eking out like all the speed in the world, sure you're fine. Okay. Hopefully that wasn't more confusing than the answer. So yeah, to first order, M is invertible. Yes. Life is always complicated though, and like, you know, bad things happen sometimes. So I want to say it in general. Okay, this is very nice. Okay, cool. All right, so let's see. We'll do the pendulum like this too. So for the pendulum, I can go stare at the stuff, we had down there and kind of figure this all out. So the mass matrix for the pendulum case, it's a scalar. It's 1D. So this is just ml squared, which if you know some things about dynamics, you'll recognize that that's the inertia, like the rotational inertia, right? So that's why the M is sometimes called the generalized inertia tensor. It sort of ends up being like inertias and masses and whatever, all kind of mushed together. The C, like times plus, we kind of just look up and kind of put everything in this format. Looks like that. The B ends up being an identity, and the G that sort of because we're using theta dot to be our velocities, that's easy. It's trivial. It's also an identity. Cool. That's easy. You can just stare at the step ahead. So just some notes on this. So it turns out all mechanical systems, so like any robot essentially, can be written like this in this manipulator form. And there's actually kind of a deep reason why. Anyone know what that is? So this is a fun bonus problem if anyone wants to have bonus points. Turns out that the manipulator equation up there, is actually just um, like a reorganizing of the Euler-Lagrange equation for a mechanical system with Lagrangian. It looks like kinetic minus potential energy. So if anyone's taken like your, kind of like intro grad level, dynamics course, we've done like Euler-Lagrange stuff. This is exactly the Euler-Lagrange equation. So if you want some bonus points, you can do that derivation and like massage it into this if you want. So right then, I guess. So this is assuming your Lagrangian looks like you have a kinetic energy that looks like this, and potential energy that I don't know, it can be whatever. So this is all right. Any questions about that stuff? Yeah. Uh, so we have to like have a particular context where it shows up to like make that conversation worth having. The place it shows up, in particular in like real life a lot in robotics, is where you've got like a rigid body where you're talking about rotations, where your pose is going to have like you're going to want to use like a rotation matrix or a quaternion or something like that, right? So really all it is the Jacobian that maps whatever you choose to be. The point is you want to choose in those situations, you almost always want to choose different velocities than your pose derivatives. Um, and the reason fundamentally is that like angular velocity is the natural choice of velocity for those things. It's what your gyro measures, right? But you can't integrate angular velocity. It doesn't make sense. If I just took my gyro and like integrated omega, it literally means nothing, like garbage. So if I want to like instead take my gyro and integrate that into like a rotation matrix, which seems like a reasonable thing to do, there's a Jacobian that you need to map omega into q dot, where q is your rotation. That's all. That's kind of all that is, right? It's saying that I have chosen to use different velocity, different coordinates for my velocity. And so there's got to be some impedance matching, like Jacobian, push those together. That's like the basic math. Because we like gyros, we like omegas, but then like your attitude representation can be kind of. And so the G will be different based on that choice. If you use a rotation matrix, there'll be one G. Use a quaternion, there'll be another G. Use Euler angles, there'll be another G. Right. Does that make sense? Yeah. Anybody else? Yeah. That's the thing that maps your controls in to the dynamics. So like in the case of the pendulum, I've got U is the torque. So it's whatever, I need. So if I wrote down my F equals ma stuff, if there's anything there in front of U, in front of the torque, that's what B is. It's just whatever's in front of the U in your dynamic. That makes sense. No. Yeah. So yeah, whatever's multiplying U in your dynamics, whatever. So you've got forces and torques in there. If whatever's in front of the force and torque term. Yeah. So we should be careful here. There's some overloading of B. B is always the thing in front of your controls. It's a little different. It's subtly different in different contexts. We always use B to mean the thing in front of your controls, whether it's force and torque or like your, whatever. In these different contexts, it can be slightly different things. But yeah, that's what it is. Is that cool? Yeah, mostly this is just like observing patterns in dynamic equations. Like you can write it in certain ways. Sometimes that's useful. Sometimes, that's kind of the standard thing. The reason we're talking about the manipulator thing is that that's like the standard way that all the dynamics packages in the robotics toolboxes work. If you go use, whatever, pick your favorite, Mujoko, rigid body dynamics JL, which we're going to use a little bit, they all they all spit it out like this. So you're going to want to know about this so you can go use one of these robotics toolboxes if you want to get the dynamics out for like a quadruped or something, which we're going to actually do in class. So you'll see this at some point if you use one of these robotics toolboxes to get your dynamics. Make sense? You don't have to know like super in depth like what's going on here. You just have to know that if I go get a URDF of a robot I like and stuff it into, this rigid body dynamics toolbox, it's going to spit out MC and D. And I need to know what to do with those things to like simulate my dynamics. So yeah, very high level. We're not going to like, I'm not expecting you to derive this or anything. It's literally like the software package you are going to use is going to spit those out. So you've got to know like how they go together and like how to use them. I'm happy to talk more in depth about it if you want to. And we can do that in like an office hours thing or recitation thing. But you don't really need to know this stuff in like a ton of depth for the purposes of the class. Cool. Anybody else? Okay. Let's see what's next. Pendulum stuff. Okay, so that's that. Okay, so the last one that we're going to do a ton of because, that's what we know how to do, are linear systems. Show of hands, who's taken a class on like linear systems theory? Not too many. So I think we're going to probably have like some crash course material on linear systems because it shows up all over controls. Okay, so these are systems that look like this. And I should say in general, they can be this version. So that's a linear system, AX times BU. So it's linear in both the X and the U. And the reason we make a big deal about this is because we know how to solve these in closed form. So, and because we can approximate almost anything like this, and that's useful. So these are called, there's some, sort of categories of these or flavors of these. They're called time invariant if they don't depend on time. So if A of t equals some constant A, B of t equals some constant B, called time varying otherwise. Yeah, these are it's almost hard to like overstate how important these are in control theory. And you have not seen these guys before, we're going to do a little bit, but you should definitely check this stuff out. And the kind of the reason they're super important is we often approximate nonlinear systems with these guys. So we would take like our x dot equals f of xu and then linearize it. So you'd have a, is df dx, which is the Taylor series, right? And then b equals df du. And now we've taken our nonlinear thing, we've locally approximated it with a linear system. We know how to solve that. We know how to do all the control things for that system. And then we'll come up with like a controller based on the linearized system. And we'll go run that controller on the nonlinear system and cross our fingers, basically. But usually it works out surprisingly well, as you'll hopefully see in this class. Like there's a funny, like one of the like, sort of, I don't know, fathers of the modern control theory field, guy Art Bryson, who's a professor in my old department at Stanford, and wrote a famous textbook called that's known as Bryson and like famous optimal control textbook. Had this like saying, "Be wise, linearize." Basically, you'll be surprised how far like linear systems, like linearizing your nonlinear thing, will take you. I kind of teased this a little bit before, right? Like those, like the quadruped stuff. Like 90% of those quadruped controllers are using a linear model, which is insane. When you look at that thing, you're like, that is not linear, but it works surprisingly well. So like this should be your first kind of course of action almost always. You should like figure out where you can linearize and try that. And it often works surprisingly well. Okay. Life advice. Cool. So any questions about like this stuff. This is just kind of like warm up stuff. Yeah. So here's the real reason it works super well in control. Yeah. So like what we're so basically you're linearizing about some point or some trajectory or something, right? In general, like you linearize at a point, right? Okay. So the gist of like how most of the stuff goes down in control is like I want to control my system to like stabilize it at a point. I'm going to linearize about the point I want to keep the system at. The controller is pushing you there. So the idea is like the controller is actually trying to keep you in some small neighborhood of the linearization point anyway. So as long as the controller is working, you're going to stay within some small region about the linearization point anyway. And so there's like this symbiosis between feedback control and linearization, right? Where like the goal of the controller is to keep you at that spot or keep you near that trajectory, right? So if the controller is working, you shouldn't be going that far away from where you linearized about. And it's only when things go really off the rails, like something breaks or you get knocked really hard, that you end up too far away, where that linearization goes bad. So that's kind of the idea. It's like in most cases, if the controller is working, then you're going to be okay, and your linearization is going to be good, right? Does that make sense? All right, cool. Okay, we've got like I don't know 10 minutes and change. So let's see. We're gonna like switch gears a little bit and like talk about the next thing. Let's see if we get through this. So now we're going to talk about equilibria, which is a super important thing. Um, so this is a point, like intuitively, this is a point where the system will like, remain at rest or something like that. Um, so this is like, the idea here is if I've got my x dot equals f of x u, what do I mean by remain at rest? X dot, like the direction the system is moving, is going to be 0, right? So an equilibrium point is where our dynamics function f of x u equals 0. Um, so you can think about this, physically, dynamically, as something where like things should stay still if they're there, if you get them there. And mathematically, you can think about this as, or algebraically, these are the roots of the dynamics, like the zeros of the dynamics function. So for our pendulum, you can think about intuitively, from like physical intuition, it's going to have two. It's going to have the one hanging down, and it's also got one up here. Or if you could perfectly balance it, right, it would stay up there, right? And then we can look at that mathematically. If I write down my dynamics here, I've got this sort of deal. This is the uncontrolled dynamics, right? So I want this to equal 0. Well, where does that happen? So trivially, theta dot equals 0. That makes sense. The velocity's got to be 0. Um, and then to get that bottom one to be 0, it's basically sine theta has to equal 0, right? So that could be theta equals 0 or pi or really, any multiple of pi. Okay, so if I write those down, right, that's sort of like exactly what we all expected. I can have the pendulum down here, or I can have it up here. Cool. So that's what an equilibrium point is. Here's a fun like brain teaser first control problem to give you a taste of like, kind of one way of thinking about control. Um, so question mark. So those are the natural equilibria for the uncontrolled dynamics. Can I move that equilibrium around with my u? What do you guys think? Can I pick an arbitrary equilibrium point? Yeah. How do I do that? Yeah. So let's do it. So let's say I want to, I don't know, let's say I want to make it pi over 2. So, okay, cool. So I'm going to write this down. So I need the following thing to be true then. Theta dot's got to equal 0, and then I've got minus g over L sine. I'll plug in pi over 2. And remember, I also have my control. So I've got 1 over ml squared u. I want this all to equal 0. So I've got to basically put that 0 here, right? So I can do that if I want to. So I've got 1 over ml squared u equals b over l sine 2. And so I've got u equals mgl. And you could probably come up with that a few ways, but that's kind of like one way of looking at these things as like control in general is thinking about how I can basically use the u in the dynamics to like shape the dynamics in the way I want. People often, you'll hear people refer to the dynamics function there as a vector field. And you can think about it like basically I can use u, plug in a feedback policy in there or whatever, and I can shape the vector field. I can like reshape the dynamics to be kind of what I want, right? So that's kind of a way to think about this stuff. And okay, so we just did it for that pi over 2 example, but in general, I could do it wherever I wanted, and we'd get a root finding problem in U. So I would have, I could set f of x to be whatever desired equilibrium x star I want, and then I would solve for the u such that this equation equals 0. Make sense? I can do that however I want to, but basically I can plug in any x star I want and then go solve for the u that makes that thing 0. And I can set it to be any arbitrary point I want. So your first control problem. Yay, we did it. Cool. Any questions about that? All right, cool. So then the last thing we're going to try to do today is to talk about now. So now you know what an equilibrium point is. Now we're going to talk about stability of equilibrium. And stability is like an absolutely like core concept in control. So this is like super important stuff. So here's kind of we're going to get at this by like, so the intuition here is when will we stay near an equilibrium point under small perturbations? That's kind of the gist of stability. So intuitively, that pendulum, it's hanging down, I can do this and it'll just hang out down here, right? All good. But up here, if I do this, it's going to fall and do one of these, right? So intuitively, this is stable, this is unstable, right? And now we're going to make that like mathematically precise. So the kind of the question is, when will we stay near point under perturbations? So here's how we're going to do it. So we're going to look at a 1D system. So when I say 1D, I mean not just the configuration, like the whole state 1D. So X is R. And we're going to draw that. So this is just on the real line. So this is super nice because I can plot like X dot versus X. So here's X dot. And I'm just going to make up a stupid dynamics function. So let's say it looks like this. Like, I don't know, some cubic looking thing. Okay, so first question is, where are the equilibria? Anybody help me out? It's where this graph crosses 0, right? So that's going to be here, here, and here. So that's all the places where theoretically I stick it right there, right on that point. X dot 0 is not going to move, right? Okay, so next question is, let's take a look at, let's say the middle one. And let's think about this for a second. If I took a little nudge to the right, what's the sign of the top? Negative. That means it's going to move forward. If I push it a little to the dot positive, it goes back. So under small perturbations here, sign of X. How about this guy? So if I push this one a little to right, X dot positive, I'm going to the right. Similarly, if I push it a little left, I'm going farther to the left, so I'm going to equilibrium point. So let's draw those things. See if I can color. So this is, if I move a little bit away, I'm going to get pushed back under the dynamics, right? So this guy we're going to say is stable. And then both of these other ones, if I get pushed away a little bit, I'm going to go off. So these are unstable. Same over here, right? So from this like very simple picture, we have like we can draw some like a really nice kind of general conclusion for this 1D picture. The thing that matters from this local stability perspective is the slope of f of x dot at the equilibrium point, right? So in particular, we find is if the slope's negative, it's stable. If the slope's positive, it's unstable. Let's write that down. So we've got df dx negative. We've got this thing stable, and then df dx positive, unstable. Cool. Okay. So turns out that simple, that's it. Like basically all there is to the story. In higher dimensions, so if you have like now you're an Rn, you got big vectors, whatever, it generalizes trivially. Anyone have any idea what happens? Yeah, so well, it's almost, right? So this thing is now is a Jacobian. And what we want now is to check the eigenvalues of that guy. What ends up happening is you want the real parts of all the eigenvalues to be positive. It's really easy to kind of, you basically the idea is you take an eigen decomposition. And when you do that, like a physics interpretation is you're decoupling this high-dimensional system into a bunch of totally decoupled one. Basically, the eigenvectors are a new basis in which you've now decoupled it into n 1D system, right? That's what the diagonal is. So now what you can do is look at the eigenvalues, which are just the slopes of the 1D systems. So now all I got to do is check the eigenvalues. Does that make sense? So that's kind of the intuition. And then you just end up with this condition. So you want real parts of all those eigenvalues. So that's stable. And then basically we say otherwise unstable. And we can do this for the pendulum. We're kind of out of time, so I'll like write this down for the pendulum. You can hang out for 2 more minutes and see that. You can leave if you want to and see it on YouTube. But we can go ahead and do this really nicely for a pendulum. We got this. I can take the Jacobian, df dx. That looks like the following. And now I can evaluate this Jacobian at the 2 equilibrium points that we saw before. So I do df dx at theta equals pi. I get 0, 1, g over L, 0. And then if I take the eigenvalues, I get plus or minus square root g over L. So I've got one negative and one positive. If any of them are positive, I'm unstable. So this guy's unstable. Okay, so let's do the other case, the other equilibrium. df dx at theta equals 0. This looks like this guy, if I take those eigenvalues, I get plus or minus I times square root V over L. What's going on here? Pure imaginary, zero real part. What can I say about this? Stable or unstable? Yeah, so marginally stable, you hear that thrown around for sort of that. So what this means, imaginary eigenvalues imply oscillations. So in this case, if there's zero real part, it means that what you've got is an undamped oscillator. What this means for the pendulum, we know that this thing is locally stable. But in general, if you take a linearization of some complicated thing and you get something like this, you cannot say anything about the stability. So what this means is that, yeah, to first order, it's an oscillator with no damping. What that means without the damping is the next term in the Taylor series is going to matter. So if you've got a second order, third order term in the Taylor series, that term might be pumping energy in or taking it out. We don't know. And so the next term in the Taylor series is really going to determine the stability. So this is inconclusive. For the pendulum, we know, but for general complicated things, you get something like this. You have to do something more complicated. And in general, that more complicated thing is Lyapunov analysis. And we'll talk a little bit about that, but that's the story. Okay, so we will say this is unstable or undamped oscillations. And that's it. If we were to, with our controller, going back to the that whole discussion about shaping the dynamics, so we could use our controller to say like U equals minus say some damping thing times theta dot. If I plug that into the dynamics and redid this, now I would get a negative real part. It would be stable. Okay, cool guys. Thanks. Welcome. Good first day. Catch you on Thursday.